Let's begin. So before we get into today's lesson, I also wanted to talk about the final, which it's next Tuesday, right? Next Tuesday? I believe it's Tuesday. So, I want to give you an idea of what the final would look like. Start there and then we'll jump into the lesson. So 2 hours, 15 minutes long. And you'll have to complete 9 problems total. Across 2 parts. So we will have part 1. This is the compulsory section. You have to do all problems in this section, do all. And there will be, I believe, 6 of the problems here. If you want, by way of topics, the things that I would want you to know is systems of equations. Meaning, know how to solve them. And also just talk about them in the sense that if I ask you about what is the rank, or what is the row space, or what is the column space, or basis for the null space, or things like that. In terms of the coefficient matrix. So that's one thing I'd ask you. Another thing I would ask you about is, well, finding inverses and using them to solving systems. Finding inverse of a square matrix. Using it to solve systems. Computing determinants. And the determinant theorems. I don't remember if I put a Cramer's rule problem on it, but you can look up Cramer's rule just in case. I don't think I put that on it. Finding eigenvalues and eigenvectors. It's going to be a 3x3 example. Then you're going to use it to do things like diagonalization. I'm going to ask you to diagonalize the matrix and find powers of the matrix. I'm also going to ask you about subspaces. Show a set is a subspace talk about its things like its basis and dimension. Change of basis problems. So that's similar to problem 3 on the take home, something like that. Where I give you some linear operation, I tell you some basis and ask you to compute this in terms of that basis. And there's also going to be Similar problem to the above in the context of 8.4. It's essentially the same thing. We'll do an example like that today. It's going to be computational. Ultimately, it's going to reduce to a system of equations, and so you'll be able to find that. So that's what part 1 is. So know about systems, inverses, determinant, eigenvalues and eigenvectors, subspaces, and these computational change of basis problems. Then there's part 2. And it's going to be a choose 3 out of 5. So you're going to do 6 problems from part 1, where you have to do everything. In part 2, I'm going to give you 5 problems. You can choose any 3. I'm even going to tell you the topics that are covered. So part 2 is going to be like the proof section. Is where you're going to show that you can prove things. So this is proofs about functions. Right, so again, similar to on the take-home, where actually to prove a function is one-to-one, then this is blah, 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 one-to-one onto isomorphisms, but in the function sense. They're not necessarily linear transformations, but in general functions. Because linear transformations, after all, are just special kinds of functions. Proofs about vector space properties. Right, so things like, is 0 times a vector always the 0 vector? Could you prove that? Right, like properties of vector spaces. Like if I know this is a vector, it belongs to a vector space, what properties will it have? You should be able to do proofs about it, like that. And kind of piggybacking off this, proofs about linear transformations in general. Transformations in particular. Again, kind of like what was on the take-home, where I asked you to prove, if we know there are isomorphisms between this and this, prove that this is an isomorphism. I can also ask you about when is it invertible, things like that. So proofs about those guys. About also proofs about matrix properties. So that's just facts about matrices themselves. You might not think of them in the context of linear transformations, but just as matrices. So you can think of that like certain things that went into proving the equivalence theorem. What are some facts about matrices? When do inverses exist? When do determinants exist? And blah, blah, blah. And the last thing is proofs about linear independence and span. And again, going through the textbook through these topics and looking at the proof problems is a good start to practice. You can also practice any problems of these types that you see from the old Math 346 finals that are on the website. But that's basically what it's going to look like. So 9 problems, 2 hours, 15 minutes, 2 parts, and that's basically going to be the setup. Yeah.
So it's going to be very much like the past finals that were posted on the website, or it's going to be more like your exam, like.
In terms of what?
As in like the past finals, a lot is like mainly computational.
It's going to look like this: 6 problems computational, 3 problems
okay.
proofs.
Like 6 problems split parts?
Yeah. Yeah, like I'd give you like one problem here, right? Find the eigenvalues and eigenvectors, diagonalize the matrix, find the powers. I'm not sure, did I do solving, know how to solve the linear differential equation? Because finding the answer is here, you can just plug and chug that answer down in all these parts. Once you do this, the rest of this is easy. In a similar way, once you solve a system, you can automatically talk about the rank, because the rank is just the number of leading ones. So to solve it, you would have figured that out anyway. So once you can do the main thing here, the rest of these kind of fall into your lap. So some of these will be with parts. Solving systems of linear ODEs, first order. All right, so we spoke about applications of eigenvalues and eigenvectors, and one of them was this, and that. But these are the hard parts. Once you find those, you just, there's a formula, there's a standard way to plug it in to get the rest. Yes?
I have a question about the eigenvectors. In your notes, I noticed that you found what x1 and x, you solved for x1, and then you had something along the lines of 2 and 1 for your eigenvector, and then that multiplied by s, and then you kind of try to make x1 into 1. So for the eigenvectors, I think I have to show you the problem, but for the eigenvectors, don't we just solve for x1 and x2 and then put it as a vector?
Eigenvectors, you're solving a system of equations, a homogeneous system.
After we do that, you did something where you took the parameter and you try to make x, you try to get rid of the parameter and make x1 equal 1.
Well, I didn't do that. There was a part where I had a vector where one of the components was a fraction, and I just scaled it to not get a fraction.
So so do we have to scale it?
No.
Or isn't
If
it
you're
the
comfortable
same?
working with fractions, then no.
Okay.
Is Kramer's rule gonna be on this?
I don't think I put it on it, but study it. What you want to put?
Yeah, then I know, might as well be.
Well, if you know how to do this, then Kramer's rule just you taking the quotients and not going to be in trouble. Any other questions?
Are you gonna give a practice final, or is it just gonna be whatever?
No, I'm giving you this.
It's just gonna be whatever examples we have on.
Yeah. So all the old finals of 346, the take-home tests, the quizzes, you can look at all these similar problems. As well as, and especially here, on this side, the proofs in the book should be helpful. So you can just go to the chapter on linear independence and span, look at the exercises, go to the back last exercises and do all the proof problems. And you should be in good shape. Yes?
None of the online finals have a solution sheet. Is it possible for you to create one for
Not
this
that,
one
not that I know of, but I'm not responsible for that. If you want one, you can ask the course supervisor, see if he has some.
Who is that?
I think it's Spielring. If you go to the Math 346 page, at the top it tells you who the course supervisor is. That person updates the website and the web page and everything. Yeah.
Are you still dropping our lowest exam?
Yes. So did everyone copy this down? So yeah, in terms of the grading system, nothing is changing. So I'll still drop 2 quizzes, 2 homeworks, 2 attendance, 1 exam.
Are there going to be any more homeworks?
You mean online homeworks?
Yes.
Yeah.
At some point you said that there would be, and then you had to post it.
I could post another one for practice, but it'll be computational. Yeah, the thing with online homework is that they can't grade proofs very well. So I can give you a homework that might help you out on part 1, but not really on part 2. So we're going to go through chapter 8, which it's very similar to chapter 4. It's just kind of rehashing things in a different context. But that context is kind of the moral of this, one of the morals of the story of elementary linear algebra, is that idea that all this stuff that we talked about with matrices, they kind of apply in this new context. So if you know a bunch of stuff about matrices, you automatically know a bunch of stuff about linear transformations. And so I'm basically going to talk about things that we can kind of know are true just by thinking of them in the matrix form. But it's nice to know it in a new context. So it's chapter 8. And I'm going to write on some useful facts, maybe some ideas how you want to think about things. But again, if you start to think of it in terms of the things that we proved about matrices, it'll make a lot of sense why certain things have to be true. So here's a function t. Let's say it's going from u to v, where u, v are vector spaces. And t is a linear transformation. What has to happen for t to be a linear transformation? Has to satisfy two properties.
Scalar multiplication and addition. It's 1-to-1.
It distributes over addition and scalar multiplication. So that means if you take t of x plus y, where x and y are vectors in U, then the output should be t of x plus t of y, where t of x and t of y are elements in V. As well as if I take t of a scalar times x, this is just a scalar times that guy. So that makes it a linear transformation between vector spaces.
Would that constitute closure under addition and scalar multiplication? And I get condition 2. Condition 1, I don't know whether or not that would constitute closure.
It's not closure, it's just a property of the function.
Oh.
Closure kind of forces you to live in the same set. Notice that here I'm talking about what's happening in U, while over here I'm talking about what's happening in V. So it's not really closure, it wouldn't be the right way to talk about it. It just has these two properties. Right, this is called the addition property. You don't need to know what it's called, you just need to know the properties. This is called the addition property. This one is called the homogeneity property. So as long as we have a function between vector spaces, and vector spaces come from our definition way back in 4.1, and as long as you have a function that satisfies these two properties, it's called a linear transformation, and it turns out we can represent these a linear transformation T as a matrix over the set of scalars that we're using. And so T of x can be interpreted as A times x for some n by n matrix A, where m is, so m is the number of rows, and that's the dimensions of your output. Dimensions of B, while n is your dimensions of U. And these guys here, of course, finite dimensional. One thing we will talk about today is how to actually construct this matrix. But it's guaranteed to be there in the finite case. So here's some more properties. So one, it's also true, you can extend these properties. So you can do something like, if you have C1 times V1 plus C2 times V2 plus Cn times Vn, you can show by induction that because of the addition property, we can break them up. And because of this, the homogeneity property, we can factor scalars out. So we can also think of this as that. So that's one property that we can break these up. Another property is that the zero vector will always map to the zero vector. And again, sort of an abusive notation, but you should always be aware of who your domain and range is. Here I'm talking about the zero vector in U, while here I'm talking about the zero vector in V. So the zero vector in the domain set will always map to the zero vector in the range set. Another property is that if we have T of X minus Y, is that the homogeneity property also applies to negative signs. This is, by the way, this is an example of something that I could ask you to prove on the final. The proofs for those actually won't be that long.
Is there like an equivalence theorem for that, or
Come again?
like is there some type of equivalence theorem? So like if I can assume the first one, like if the first one is true, do the others have to be true, or are they all not related?
If you know T is a linear transformation, then yes, it will break things up like this. Because it has these two properties.
Would it also affect the other bullet points?
Yeah, this is always true for a linear transformation. Yeah. These have to hold. One, you can realize it has to hold because T I can think of as a matrix. So if I take, plug in X equals 0, the output is going to be the 0 matrix over the field. Right? There are other properties. We can actually just write 0 as 0 plus 0 and expand it here, and then use the vector space property to show that, oh, T of 0 changed nothing. So there are a bunch of ways. This guy I can write as plus minus 1 times this, use this property to expand it, and then show that since T of Y is an element of a vector space, minus 1 times it is the negative of it. Yeah?
Left side of the board, you say that T is a linear transformation if and only if.
Yeah, as in I'm doing a definition.
So that's just a tautology.
Yeah, it's a tautology. Meaning if it doesn't fulfill these properties, it's not a linear transformation. If it's a linear transformation, it will fulfill these properties. It's how we name it. So it's a function that has these properties, we call them linear transformations. And as I sort of hinted here, a useful idea is to remember X and T of X, or something similar, are elements of vector spaces. So if I know something is true for any element of a vector space, it will be true if I'm talking about T of X. That will also hold. Vector spaces. And T can be represented by A. Right? So for example, if you know that the dimensions of U and V are the same, then you automatically know that T can be represented by a square matrix, and that would mean if I can find its inverse, the function is invertible, the function is one-to-one. A lot of things follow for free, just by having that conceptual between. So you can kind of switch between the two ways that we've been thinking about things here. You can switch to the matrix perspective and switch back to the function perspective, and they're equivalent in a lot of ways. Here's another useful concept. If we have, for example, T Fn to Fn. F represents, it can be the real numbers or the complex numbers. And then we can think of A, the matrix A that represents T, as this matrix. This is called the standard matrix. And it's called the standard matrix because it's in terms of the standard basis on Rn. So you can think of it as looking at what T does to all the basis vectors on Rn and throwing them in columns. So if you can figure out what the operation does on the basis vectors, you can actually construct the matrix using that formula. Moreover, by stuff we saw in chapter 4, I can also talk about that matrix being in terms of a basis B, which we usually say T is written in terms of B, and that will be the matrix of T of the basis vectors in terms of B. So you can always change the basis if it's convenient for you. And that's how you'd actually construct it. Let's do some examples relating to 4.9. So this, in 4.9, we kind of skipped it. We didn't really talk about the geometric interpretations. We were more focused on, theoretical and computational ones. But you can apply it to the geometric situation if you want, just by looking at what it does to the basis vectors. So, for example, if we look at rotation by an angle theta, for example, right? It turns out that that is a linear transformation, which means there exists a matrix that I can write down that would represent that operation being done. So let's say I can have T from R2 to R2 that does this operation. What would such a matrix look like? So it's a linear transformation, which means there has to be some matrix. So all you have to do is, by this idea, which is a very useful idea to have, is figure out what T would have to do to the basis vectors. We know that the standard basis for R2 is the I vector and the j vector. So if I can figure out how a rotation affects I and j, I can figure out how a rotation will affect everything. So if you look, for example, at the I vector that goes here, and let's say I wanted to rotate that by an angle theta. Right? What would that actually happen? What would be the new coordinates of this vector? Well, you can notice that here I can create a right triangle. So what would be the y coordinate of this guy? Sine theta. And what would be the x coordinate of that? Cosine. Right? So I can actually change I. So that means under a rotation, my I would change to the vector cosine theta, sine theta. And then I can look, for example, what happens to the j vector. Right? If I rotate by an angle theta to get a new vector, what is the coordinates now? Right? What would the coordinates of this guy be? The x coordinate would be what? Negative sine theta. And the y coordinate would be? So this means my j vector would map to minus sine cosine, which means my A would be the matrix that translates I and j, and hence it would be the matrix cosine sine and minus sine cosine. So when you read 3.4.9, for example, and they tell you, this is how, these are the matrices that represent this kind of operation in the plane. So if you want to rotate vectors, multiply by this. Why did you have to multiply by that? They applied this idea. They looked at, okay, figure out what operation you want to do, look at what it does to your basis vectors, throw those guys in a matrix. That matrix represents this function. So the operation of rotation by an angle theta is this 2 by 2 matrix when I'm going from R2 to R2. So we can think of a lot of any linear transformation in terms of a matrix, and this is kind of the idea of how we would construct that matrix. And so now if you want to use linear algebra to study rotations, we would be working with this matrix. If we want to study rotations of counterclockwise rotation by some radian theta. So now if you can go back, and we also already spoke about projections. Projections would be the same idea, right? We saw that the projection was 1, 0, 0, 0 to project down to the y-axis. And the reason for that was you wouldn't change the x-coordinate, so the I vector stays the same. But you'd make the y-coordinate 0 so that it lands on the x-axis, so that's why your j vector, you turn it to the 0 vector, right? You would have that same idea. And, oh, by the way, I can make sure you know the list of linear transformations. And again, this is more 4.9 stuff. You should mention them even though we didn't focus on it. We can apply this reasoning to all the geometric linear transformations. And these are rotations, reflections, dilations, shear, contractions. And scaling, I think. These are all the linear transformations. If you do anything else to the vectors in a plane, other than something that's on this list, it's not a linear transformation.
Well, translation.
Huh?
Translation.
What?
Translation.
No, translations won't work. Why wouldn't the translations work? If you're translating something, you'd mess with the 0 vector. In other words, like things that pass through the origin wouldn't pass through it potentially. Yeah.
So then like any linear transformation, if it's sort of its domain is a vector space, then its output is by necessity also a vector space.
No, it's that we wouldn't call it a linear transformation unless that were the case. Like when someone says to you, I'm looking at a linear transformation, you would automatically assume that, okay, the domain is a vector space and the range is a vector space, and it satisfies those two properties. So if your domain, if either your domain or range is not a vector space, you wouldn't call it a linear transformation. It would be wrong to call it that. You'd call it something else. It's some other kind of function, right? And there are many other kinds of functions. And there are times when even the names of functions that we have here, like if I say something like an isomorphism, there are contexts in which you would have to emphasize it's a vector space isomorphism as opposed to some other kind of isomorphism. Because different functions have different domains and ranges, and they preserve different properties, and so you have to be careful, right? So that's important. So we're not going to talk about the other guys here, but you should know that they do exist out there. There are many functions that preserve properties that we care about. Linear transformations preserve the properties of vector spaces. Meaning it doesn't mess with your addition and scalar multiplication property of vector spaces. I might want a function that preserves some other property, and then I need some other kind of machinery. It's not a linear transformation anymore, I need something else.
Wouldn't like a dilation be similar to like a scalar multiplication, where you're just increasing the
It's like spreading out according to the origin.
Yeah.
What else do we want to do? Let's say more useful facts. Let's say V1, V2, V3 is a basis U, where T goes from U to V. And T is onto, let's say you know that T is onto, it also means that the set of outputs here will actually form a basis for the output space. And that's something you can assume. You can use it without proof. Also, T is a linear transformation. The following facts are true. And again, literally every fact that I'm writing down here is something that in our matrix interpretation, we're just translating into a different language. But you can, all of this will connect to matrices somehow. A lot of the time it's connecting back to the equivalence theorem, which the list of things I'm going to talk about now is also connecting directly back to the equivalence theorem. So let T, this, then, say T is from U to V, then A. If I look at the kernel of T, is a subspace U. The range of T is a subspace V. Right? And for example, part A is really just saying the solution to a homogeneous system is a subspace of the set of domains, which we kind of knew from matrices, but I'm just kind of restating it in terms of linear transformations. Right, so all of these, they have a matrix background to it. If RT is finite dimensional, the rank is equal to the dimensions of R of T. That's kind of like me saying the rank is equal to the number of rows. D, the number of non-zero rows. Nullity, remember this is the dimensions of the number of basis vectors for the homogeneous solution. So the nullity of T is equal to the dimensions of the kernel. We also can, that dimension theorem, we can talk about the rank of T plus the nullity of T. Is equal to the dimensions of U. And that's the dimension theorem that we spoke about in terms of matrices. So it's really just like a translation. Facts that we kind of know, and we can always translate back to matrices and prove them there. But chapter 8 just brings them to the forefront because knowing them on this level is nice, that you don't want to always have to go back and retranslate everything. How about 8.2? This spoke about compositions and inverses of linear transformations. Right, so inverses of functions is kind of like finding the inverses of a matrix. Compositions is matrix multiplication. Right? So we can think about compositions between linear transformations as some sort of matrix multiplication. This is basically the idea. So important theorems here. That's T from U to V be a linear transformation. And the following are equivalent. T is 1 to 1. E. The kernel of T is only the 0 vector. And T is onto at the same time. We have that for free if the dimensions of U is equal to the dimensions of V. Otherwise, you cannot assume onto. That part is important. It's not always the case. It's the case if your dimensions are the same. Other useful facts. This one, I feel like I mentioned it before. It's probably a repeat. This feels very familiar. So let's say I have T1 that goes from U to V, and T2 goes from V to W, are linear transformations. Then T2 of T1, this goes from U to W, is also a linear transformation. It's also a nice thing to prove. But you should be able to prove that. It shouldn't be too much trouble. Another thing, if T1 is represented by A and T2 is represented by B, then turns out T2 composed of T1 is represented by the matrix BA. The product will represent the composition. And it turns out that compositions preserve invertibility as well. So you also know that if T1 is invertible, meaning you can find a function that's a linear transformation that goes in the opposite way, and T2 is invertible, then so is T2 composed with T1. In fact, the inverse of the composition also follows the shoes and socks law. You take the inverse composed in the opposite order. So let me actually number these. Let's call that A. Let's call it B. Let's call something C. If T1 and T2 are 1 to 1, then the composition is also 1 to 1. Be able to prove these. So those are the important facts for 8.2. So these are ideas that will come in handy. One, three. So more important ideas here. So T is a linear transformation. T is called an iso. And we can put in parentheses a vector space isomorphism. If T is 1 to 1 and onto. And isomorphisms are super important. We can preserve all sorts of things, not just vector spaces. So, I don't know if any of you took abstract algebra, for example, or something like that, but you can talk about isomorphisms of groups, isomorphisms of rings, of fields, all sorts of things. And some things will have nice carryover, but not everything. Also going to tell you how to translate some things here. By the way, I forgot the root language, it's probably Greek, but isomorphic means the same form. So it is an idea that we can apply to various types of mathematics. In this case, our isomorphism is relating to vector spaces. So that is, i.e., if U and V are isomorphic, and this was part of the take-home test as well, then there is an isomorphism T that goes from U to V, and at the same time, U and V are mathematically indistinguishable as vector spaces. Meaning there's no real difference between the two, probably notation. One set is exactly the same as the other and will function exactly the same as the other. You're just pretty much changing the names of all the elements and nothing else is changing. So in that sense, in fact, we kind of have a theorem here. Let's say that. Every n-dimensional vector space over F is isomorphic. That means that's the set of scalars, the field of scalars is isomorphic to Fn. Every n-dimensional vector space will be isomorphic to Fn. In fact, we kind of know how. So let U be a vector space of dimension n, then T from U to Fn given by the coordinate map. Right? That means I order the basis of this, take any vector, find its coefficients, and output to that coordinate in Fn, and I would have created a one-to-one and onto linear transformation by doing that. Is an iso, i.e. T of x equals x, the coordinate map of x will be an isomorphism. So let me show you some examples of that. Example. And we've been using these things, I'm just stating it in different language. M22 is isomorphic to F4, for example. The set of all 2x2 matrices, we know that forms a vector space. It turns out that they are isomorphic to F4 or R4 equivalently by doing actually the coordinate map. So if I take T of A, B, C, D, I can actually output that to the vector A, B, C, D. And I can think of every 2x2 matrix as a 4-dimensional vector in that case. And so whatever I can do with a 4-dimensional vector, I can do with these matrices. This is an isomorphism. Another example is a set of polynomials of n degree is iso n minus 1 to nice notation to Fn by if I take T of A0 plus A1x plus da 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 plus An minus 1 x n minus 1, I can output that to the vector A0, A1, An minus 1 is an iso. Right? You can prove that this kind of function is one-to-one and onto, and it's a linear transformation. It will preserve sums and scalar multiples. So the coordinate map that we introduced, I forgot what section, is a very important map. It actually is a map that tells us how to form isomorphisms between general vector spaces and Rn, or Fn. And so also in the take-home test, we proved that if x was isomorphic to y and y was isomorphic to z, then x is isomorphic to z. So the fact that you can prove that any vector space is isomorphic to Fn is also, any n-dimensional vector space is isomorphic to Fn. It's also true that any n-dimensional vector space is isomorphic to any other n-dimensional vector space by transitivity. Because I can connect them both to Fn, and then the composition can jump between any two vector spaces. So all n-dimensional vector spaces are the same set. It's just changing the names. And this is very powerful, because if you know a lot about one of them, you know about all of them, right? If I know everything, if I know all there is to know about the set of 2 by 2 matrices, I know all there is to know about any other fourth dimensional vector space. It's just a matter of figuring out who got renamed what. And so there's one thing I want to take from 8.4. This talks about matrices as linear transformations. This repeats the idea that I can represent a matrix that represents a linear transformation as just looking at what it does to the basis vectors. And gives some important examples. There are two. And you use both of these in the take-home test actually, but again, chapter 8 is just a rehash of chapter 4. Now, I want to do an example here. That it amounts to setting up systems of equations to solve it. So I already pre-solved it and we're just going to go through the motions here. So a problem like this has shown up on several 346 finals. So it's something that we think is important. In fact, I think the example I'm going to do now is actually from a final. So let L from R3 to R3 be a linear transformation. Okay, what are some things you can tell me about L right away? How can I think about L in a linear algebra context? So we gave me a linear transformation from R3 to R3. If I plug in this vector, that's the output. Plug in this vector, that's the output. Plug in this vector, that's the output. And part A says find L of 2, 3, 4. And part B says find the matrix that represents L with respect to the basis 1, 0, 0, 1, 1, 0, 1, 1, 1. These three matrices form a basis for R3. So how would you go about solving this? There are actually a couple ways, but
Combine all the matrices to form a 3x3 matrix.
okay. So that was the answer to the question I asked earlier. Like, what could you tell me about L right away? The fact it's a 3x3 matrix. It can be represented by a 3x3 matrix, and that's what I'm going to use to solve this problem. I'm going to realize that L can be thought of as a 3x3 matrix, and so I can take a 3x3 multiplied by this, that's the output. If I take that 3x3 multiplied by this, that's the result. If I take the 3x3 multiplied by this, that will be the result. So we can solve it that way. There are several other ways. I think this is conceptually the easiest way to do it. And more straightforward, probably not the shortest way, but it's not too terribly long either. So the idea is set L to be, set the standard matrix to be some 3x3, A, B, C, D, E, F, G, H, I. And if we knew, for example, this was R2 to R3, what would it be? What would it look like? If the domain was R2 and the output was R3, what kind of matrix would it be? No. 3 by 2.
3 by 2.
Remember, the number of columns tells you the input dimension, the number of rows tell you the output dimension, so that's important. Here, either way you thought about it, you would get that it's a 3 by 3, but in the event that it's not, in the event that these dimensions are different, you have to know what size matrix would represent this. Okay. So I would set that up, and then this would mean if I take A, B, C, D, E, F, G, H, I, and I multiplied it by 1, 0, 0, the result was 5, 0, 0. This actually implied that, and I actually did the multiplication, so I'm just saying, this is A, D, and G. And that was equal to 5, 0, 0. So that immediately tells you A is 5, D is 0, G is 0. And then, if I take that same matrix, multiplied it by 1, 1, 0, the output was 6, 6, 0, which means if I take this, multiply by that, I would get A plus B, D plus E, G plus H. And the thing is, I already know A, D, and G, so I can find B, C, and H. That would be 6, 6, 0. And it's also true that if I take A, B, C, D, E, F, G, H, I, multiplied by 1, 1, 1, the result is 7, 7, 7, which means I would have A plus B plus C, D plus E plus F, G plus H plus I should be equal to 7, 7, 7. And ultimately, we get the fact that, right? Solve for ADG here, plug it in here, solve for BEH here, plug both of those in here, solve for the CFI, and ultimately you get that the matrix is 5, 1, 1, 0, 6, 1, 0, 0, 7. Which means, if I want to find L of 2, 3, 4, that's just equal to this matrix times 2, 3, 4. Which is 17, 22, 28. So we need to find this guy in terms of that U basis. So what I'm going to do is I'm going to use the idea that I'm going to translate what L does on the old bases and write those in terms of the basis B. And so this means I want to write 5, 0, 0 in terms of basis B. I also want to write 6, 6, 0 in terms of the basis B. I also want to write 7, 7, 7 in terms of the basis B. You can set up a system of equations for that, and it will actually give me 5, 0, 0, 0, 6, 0, and 0, 0, 7. Because you realize this guy is just 5 times this guy plus 0 times this guy plus 0 times this guy. So that's 5, 0, 0. And this guy is actually just, yeah, 0 plus this guy, 6 times that guy plus 0 times that guy, and you get this guy. So on and so forth. An alternative to B, you could also find the change of basis matrix. So that means you put you augment the old basis and the new basis, and then you do the reducer echelon form. So you get I3 here, and so that would be 0, 0, 1, 1, 0, 1, 1, 1, and put here 5, 0, 0. 6, 6, 0, 7, 7, 7. That would reduce to this guy. And then you can pick out the answer from here. And we can stop there. Chapter 8 is really just a retranslation, well, a translation of chapter 4. Stop there. That's it. But this problem itself is an important kind of problem. I'll put something like this on the final because it's not terribly difficult to do. So might be some free points for something. We'll stop there. The final is Tuesday, and I guess I can. Homework extra practice.
What time is it?
Don't forget to leave your
What time is the final?
I believe I sent an email.